When you execute a deployment today, the application is live in a fraction of a second. Compare that to the alternative we relied on for a decade, the virtual machine. To isolate a 50-megabyte application, a virtual machine requires you to boot an entire redundant 2-gigabyte guest operating system. You pay a 45-second startup penalty just to give your code a place to run. But here is the paradox of modern DevOps. We rely entirely on containers to solve this deployment bottleneck. Yet, if you look inside the Linux kernel, there's no native first-class feature called a container. The container, as a discrete entity, does not actually exist. It is simply a standard Linux process wrapped in a carefully orchestrated illusion. This illusion is constructed using exactly 3 native Linux C primitives: namespaces, control groups, and overlay-fs. Treating containers merely as lightweight virtual machines limits your engineering potential. Mastering system architecture requires understanding how these specific kernel primitives are manipulated at the system call level. The earliest attempt to isolate a process dates back to Unix version 7 in 1979 with a system call known as chroot. Chroot changes the apparent root directory, blinding the process to the real host file system above it. But this creates zero actual isolation. The proc file system remains globally readable, allowing a jailed process to query, map, and signal every application running on the host machine. It also shares the host's networking stack entirely. A jailed process can intercept traffic on shared interfaces and bind to any port, creating immediate conflicts with other running services. If that jailed process is running as root, the isolation is trivial to bypass. By compiling a C program to create a nested directory, entering it, and looping upward through a series of ... commands, the process executes a path traversal and breaks completely out of the boundary. Masking a file path is a fragile facade. Genuine multi-tenant security requires the operating system to enforce strict boundaries deep within kernel memory. To enforce these boundaries, Linux developers introduced namespaces. A namespace wraps a global system resource in an abstraction, altering what a process can see and interact with. These side-by-side tables illustrate how the kernel maintains 2 simultaneous realities using a struct called ensproxy. On the host machine, the global namespace sees an application as process ID 4821, but inside the isolated PID namespace, that same application believes it is process ID 1. This dual mapping controls the container lifecycle. When a container runtime like Docker detects that process ID 1 has crashed, the namespace is empty. The kernel destroys the namespace, and the container dies. The kernel applies this exact same logic to the network stack. A network namespace provisions a completely dedicated, isolated set of interfaces, IP addresses, and routing tables from scratch. To connect this isolated space to the outside world, the kernel establishes a virtual Ethernet pair. Think of this as a virtual physical cable. One end is placed inside the container's namespace as ETH0, while the other plugs into a virtual bridge on the host OS. From there, standard NAT rules via IP tables route external traffic from the host's public IP address directly across that bridge and down into the isolated namespace. Because each network stack is fully independent, the port conflicts of the early 2000s are eliminated. 50 distinct microservices can all bind to port 8080 simultaneously on a single server, with zero overlap. Namespaces restrict visibility perfectly, but they do nothing to restrict resource consumption. An isolated process can still consume 100% of the host's CPU and memory. This is solved by control groups, or cgroups. The kernel exposes these controls as a virtual file system mapped to /sys/fs/cgroup. By writing a simple integer into a file like memory.limit in bytes, you impose a hard mathematical ceiling on a process. To see why this matters, consider the noisy neighbor problem. If 10 microservices share a single server and one payment service develops a memory leak, it will aggressively allocate RAM until the hardware is exhausted. Without cgroups, the host operating system panics. The out-of-memory killer fires blindly, often terminating critical, unrelated user-facing services just to keep the machine online. With cgroups in place, the dynamic changes. When the payment service attempts to exceed its allocated limit, the OO killer fires locally. It snipes the specific runaway process inside the cgroup boundary. The innocent services never notice a drop in performance. By containing the blast radius of runaway code, cgroups guarantee service levels. They upgrade containerization from mere visibility isolation to structural predictability. Now we have isolated compute and predictable limits. But if you boot 500 containers, and each requires its own 77 megabyte base OS, you waste nearly 40 gigabytes of space on identical files. The solution is OverlayFS, a union file system that merges multiple directories into a single unified view. The bottom layers, called the lower tier, hold your read-only image components. Because they cannot be modified, a single 77 megabyte Ubuntu base can be safely shared by thousands of containers simultaneously. The upper dir is a completely empty read-write layer unique to each running container. If a process needs to modify a base file, OverlayFS intercepts the system call. It copies the entire file from the lower layer up to the writable layer and applies the change there. The base image remains completely untouched. This is called copy on write. This architecture makes containers deliberately ephemeral. When you stop a container, the runtime deletes that upper directory. Every runtime modification is permanently destroyed, while the pristine base layers wait for the next boot. This copy-on-write mechanic dictates how you engineer your build pipelines. Because altering a base layer invalidates every cached layer stacked above it, static operating system dependencies must always be installed before your rapidly changing application code. Let's trace exactly what happens inside the kernel the moment you execute docker run nginx. At 5 milliseconds, the engine unpacks the image tarballs and mounts the OverlayFS directories, establishing the merged root file system. At 15 milliseconds, Docker executes the clone system call with strict namespace flags. The kernel instantly partitions the process ID and network views. The application is now running in an isolated reality. By 25 milliseconds, the engine traverses the host's /sys/fs/control group directory, writing precise integer limits for CPU and memory usage into the control files. The newly formed process executes pivot root to trap itself inside the overlay file system. It proactively drops its raw Linux root capabilities, blocking any chance of escaping to the host kernel. At 45 milliseconds, the host machine writes the final NAT IP tables rule, patching the container's isolated network stack to the outside world. The process is now ready to serve traffic. To the developer typing the command, the application simply appeared online instantly. But underneath that illusion, a functional container is nothing more than a standard process, perfectly restricted by these interwoven C primitives in under 50 milliseconds. We have constructed the perfect isolation bubble. But Docker is inherently designed to solve a single host lifecycle problem. It is strictly an imperative tool. It executes a command to run a process, and it stops. It possesses zero awareness of external hardware or clustered environments. In production, the physical host might lose power. A localized memory failure could crash a node. Unpredictable traffic spikes might overwhelm the available CPU on a single machine. Operating at scale requires shifting from an imperative command line to a declarative desired state model. This is exactly why Kubernetes exists. Kubernetes does not replace namespaces or cgroups. It acts as an aggressive thermostat across your entire data center. It runs reconciliation loops thousands of times a second, reading the current state of every node and constantly rescheduling containers to ensure reality matches your declared topology. You cannot orchestrate what you do not comprehend. Understanding the atomic physics of a single container, the precise limits of its file system, memory bounds, and network views, is the mandatory prerequisite to mastering the planetary scale chemistry of a Kubernetes cluster.